greatly organized conference in a very nice location. And I know that the lunch is coming soon, and it's the end of the conference, so I'll try to keep you brief. So today I will talk about our recent efforts at Microsoft Station Q to do numerical simulations of Majorana nanowires and what we have achieved so far. So this work is done by this gang of people here, and you've seen most of them here. And so, well, we're all working at Microsoft Station Q. And of course, I should thank Silas a lot for giving a nice introduction into the subject just a talk ago. So I will only briefly recap that we have Majoranas in P-wave superconductors. And since the experimental progress actually kicked off since the proposals in these two papers, which gave a very simple toy model prescription of how do we actually observe Majorana in nanowires, that is that we attach a superconductor to a semiconductor with a large spin orbit coupling, and then we tune the magnetic field, and at some moment we see a topological transition in which we see the nanowire at the end of, Majorana at the end of the nanowire. And so since then, this is actually a remarkable thing on its own, because I'm actually giving a very beginner introduction because I've been working in a different area before. And unlike, say, for example, high-TC superconductors, the progress really kicked off from the theoretical proposal. And so then the experiment picked off, and we could see the zero bias peaks pretty soon, and then the incremental work on improving the quality of the systems, for example, getting the hard superconducting gaps in indium arsenide aluminum nanowires, then observing the correct periodicity with the change of magnetic field, as well as finite size scaling of Majorana oscillations, was taken over. Sorry, was done. We have a large poisoning times in the systems, and large conductance, as we've recently learned, as well as a lot of control using quantum dots and applied gates. And so now we're at the stage where we can, this works, safely assume that we have a vast array of supporting evidence for having actually Majoranas in nanowires, so we have to do something further with them. And similar to as before, the theoretical progress is not standing, so we have new proposals for further directions what we can do. So we can do qubits networks, we can try to simulate protocols, and try to build a quantum computer. You know, Karsten, I think, just showed his quantum computer, which he's not going to sell to us. And so at this moment, I have to say that actually, I mean, this is complicated. Any future implementation of this would rely a lot on us being able to provide quantitative prediction for what's actually happening in these nanowires. The simple example is, you know, experimentalists come to you and says, hey, I have a critical field 1.5 Tesla instead of 1 Tesla. What is going on? And the only way you can address this is to build some numerical model and simulate it, and then say, okay, well, I think it's like this. But okay, let's talk about what is the model that we should have. What should it include? And we should have orbital effects of magnetic fields. Ideally, we want to incorporate all the materials that we have, indium arsenide, aluminum, many others. We have to take care of what's happening at the interface of the systems. We maybe should use disorder, figure out what do we do with the gating, some transport, it turns out into a mess. And even if we reduce complexity and get into some kind of time-binding model, these time-binding models are actually pretty big and typically only concentrate on a specific aspect of a problem. So I will also concentrate on a specific aspect of a problem, and I'll say what are we actually caring about. If we want to build a quantitative description, in this case what's happening in the wires from Copenhagen, well, first it's important to see that we have a pretty clean interface. This is taken from this nice material paper from Peter Krogstrup and was actually shown here last week. So we have clean interfaces, so we can assume that we don't have too strong of a disorder in the problem. If we look at the dependence of the conductance we see on the magnetic field, we see that the induced gap in the nanowires is actually pretty large. It's almost as large or close to the bulk gap of the aluminum. And there's a lot of degree of control using gates into the systems. For example, we'll have this large number of we have a quantum dot at the entrance and gates attached to the problem. And for example, this was sent to us by Mingtang, that exact example. Hey guys, we have some strange dependence of a G factor, where a G factor is, you divide the induced gap in the system over the critical field. That's like the rough approximate for Zeeman splitting into the system, and it looks something like this. Can you tell us what's going on? All right, but let me first say, how are we actually building models for Majorana nanowires? And typically, since if we want to reduce complexity, what we want to do is we want to get rid of a superconductor in any way. So first thing one can do is just say, okay, well, I have some induced gap into the problem, let me just put it in. But then what happens is I'm not quantitative. I don't have any renormalization of the parameters in the systems, because what I would expect is, for example, if I proximatize to a superconductor, my magnetic response is changed, and this doesn't happen in a model like this. So what one can also do is we can try to integrate out superconductor, and that's a better approach, because in this way we can renormalize all our effective parameters in the problem, such as the Zeeman splitting, spin-orbit coupling, or chemical potential into the system, and we can find, for example, what is the induced gap in the problem as a function of a parameter that describes the coupling of a superconductor to a semiconductor, this effective strength coupling gamma. And so if we do that, we can then estimate all the important observables in the system, such as critical fields and coherence length. The bottom line is that no matter what we do, the coupling to the superconductor is described by this one single parameter gamma. So why this is not enough and why we want to do something different? Well, first of all is since integrating out superconductors work well in the weak coupling limit, and if our coupling is strong, well, we have a problem because the renormalization might be very, very different. Second is that at the interface, so if we throw out superconductor, there are effects happening in the interface, for example, such as bed bending that I will show later. That is not included anyhow. And then we have actually a really thin superconductor in the problem, which, in the geometry that I will cover here is something like 10 nanometers. And so at this thing, it has a discrete set of modes. We can't just get rid of it. And finally, I don't think I wrote it here, but we might expect that the probability density may shift across the interface and being more localized in one or the other part of the problem. And so what we wanted to do here is we wanted to understand what's and how does the interface between superconductor and semiconductor work, and then try to get some understanding of the effective model that we have to put in later, and try to see if we can actually help experimentalists anyway. Now, at this moment, I have to say a disclaimer, it's a work in progress. Now, one needs to give a credit where credit is due. There is a great project called Quant developed in Delft, and we had a lot of help doing simulations using that. And one technicality is that in order to take into account the system of this size, one has to impose a very different discretization steps of this effective KP model in different areas of the problem. Okay, so fine, we can, I'm sorry, I will come back. So this is the model we're trying to solve, right? So we have all the tunneling, and we have the spin-orbit coupling in the semiconductor, magnetic field, and superconducting gap. So let's try to use this and try to simulate something. And then as soon as we simulate, we should, and we put the right numbers for the sizes of the system, we'll see that we have a set of modes that are the set of subbands in the semiconductor that are split by a certain distance. And then on top of that, with this geometry and this effective mass, we have the superconducting bands, and the spacing between the two is actually very much different. So why do we care about this? Well, we care about this because if we now start shifting these bands around, the tunneling between the bands would only be strong in the very tiny points of this parameter here. So we can't really, for example, make a strong proximity between semiconductor and superconductor generically, which means we cannot open a large induced gap that happens in the experiment. And so this is a problem. Now, at this moment, I want to emphasize is that these numbers here, the spacings between the subbands in the nanowire structures, are actually much bigger than the gap in the problem, than the bulk gap, and so we shouldn't expect multiple subband physics to enter, and we should expect to see one Majorana in this problem. So the ingredient that we missed actually, so one can say, okay, well, so what can happen to induce a large gap in the semiconductor? It could be disorder, because in this case I lose the conservation of my momentum in the direction parallel to the interface, and that could help to match different modes of the system. But if we have that, we probably won't have Majoranas. So what one ingredient that we miss is actually the interface physics, and that is the band bending at the interface. This is taken from some textbook in the problem. So if we have a metal on one side, which is the aluminum, and we have the indium arsenide, which is an N-type semiconductor, we expect to have an accumulation layer at the edge. So let's try to model this. What we're going to do is we're going to put some Thomas Fermi screening into the problem, and this is the profile that we will have. And once we have this, of course, the first outlook of this is that all the eigenfunctions of the problem get shifted towards the interface. And we would expect that that would help to penetrate more from the superconductor and semiconductor and give a larger tunneling between the two. And this turns out to be true. So this is the same plot as shown before, but now at different values of the screening potential. So at 0, I have a very sharp condition to induce a large gap in the problem, but I can relax it more and more once I have a larger potential at the edge. So side note, so we now don't have such a strong resonant condition to induce the gap. This also works in case if we don't study the lowest subband of a semiconductor here, we open the gap simultaneously for all of them. So okay, so now that we learned that we can actually, that the interface is important to induce the large gap, and we have a strong tunneling between the subbands in the semiconductor and the superconductor, let's try to understand what's actually happening in the system now. And what is happening, and one immediate consideration one has to take is that, well, if we have the strong tunneling between the subbands, now the subbands are hybridized, and of course, depending now on the value of the chemical potential, I have more semiconducting or more superconducting-like state. For example, here in this upper subband, I would be very superconducting like at the bottom, but once I change the chemical potential, which means I apply some gate voltage into the problem, the nature of the state, the nature of this band would actually change. And what I should expect is that the coupling to the superconductor actually changes with the application of the gate voltage. And so if I do this, so here we're studying, I think, the lower subband here. So we apply this gate voltage. Indeed, that is the case. The gate voltage as a function, sorry, the tunneling, the coupling constant to the superconductor increases as a function of, well, changes with the gate voltage once we go higher in the subband. And we can correlate this to this quantity here. So what we do is we just look at the eigenfunctions of the system, and we calculate the probability to have a state in the superconductor. And this is a number somewhere between 0 and 1, and these two numbers are directly correlated. The more we couple the two, the more weight we get into the superconductor. Okay, so now what happens with the actual Majoranas in the problem? Well, if we now apply a magnetic field and we induce a Majorana somewhere at the edge of the system, what happens now is this Majorana is actually split to a large proportion between the semiconductor and the superconductor, and so we should expect that something new is happening. And so what is happening is the following. Now let me come back for a second and show you the picture of the subbands of the system. If I now move the occupation up and down, what I should see is that I move, as I said, I move more between superconducting and semiconducting-like states. So what I can do is I can look at the minimum gap in the problem. That would be my induced gap at 0 field, and that would be the gap or topological gap in the at finite magnetic fields. And so if I look at this, I would see something different as compared to the standard model of integrated superconductor, which is that my critical field changes with the application of the gate voltage, but also my coupling does change as a function of this gate voltage. And that's the important, actually, outlook for analytical understanding of the problem, so the models in which we have a constant coupling might need to be, well, in several, so it might be important to refine this coupling constant gamma. And so if we now put this all into one plot, so this is the induced gap as a function of the gate voltage in the problem, and at the same time the critical field. We can divide one over another and get something that's pretty similar to what the experimentalists see. Now, I said this is a work in progress. We're working out the numbers at this moment, and we're heading in that direction. And actually, at this moment, I would finish this and say, well, we now have a model that have an equal footing of the semiconductor and superconductor. We learned how to get large induced gaps, and then the interface physics is very important in the actual quantitative numerical simulations. And then we can see how the application of the gate voltage changes the, well, fundamental properties of this Majorana nanowire, such as that now we cannot describe it by one parameter theory. And then there are, of course, future directions, and the important one is to actually obtain the self-consistent charge and to eliminate this Thomas Fermi approximation, and that's something we're working on now. Thank you very much. Well, I mean, the lunch is like now, right?